Okay, so physics unit, first thing we talked about types of energy, right? So that's mostly going to be in the multiple choice. Okay, the types of energy that we covered, okay, we talked about chemical energy, nuclear energy, solar energy, electrical energy. We just went over the types. Okay, we looked at a few examples of technology that use or make those types. We looked at Volta's pile, right, the first battery, and we looked at, you know, a couple of like Orsted's thing with magnetic energy and the compass and all that kind of stuff. I'm not worried about people's names on the final, but do be able to recognize a type of energy in a multiple choice question. So if I ask you something like what I asked on your unit exam about what kind of energy is possessed by a rolling bowling ball. Okay, well, if a bowling ball is rolling, it's on the ground, right? It could have, one of the correct answers could be mechanical energy or kinetic energy, okay? But it wouldn't have any potential because it's on the ground, and it wouldn't have any chemical because it's not going to catch on fire. Everyone follow? Okay, so be able to identify energy types from a multiple choice kind of question. All right, so it's just general recognition. That's what you, so read over your notes. Okay, those are the ones that were like out of the textbook. Okay, they look like they're out of a textbook because they are. Okay, and then we talked about thermodynamics. Okay, there were 2 laws of thermodynamics that we covered. Anyone remember what the first law of thermodynamics was? We talked about it quite a bit in this unit. In fact, we had some problems to do with it late in the unit. It's the law of conservation of energy. Okay? First law of thermodynamics is the law of conservation of energy. The second law of thermodynamics tells us which way heat travels. Heat travels from hot to cold or from high energy to low energy. Right? So those are things that we will definitely need to know. Not so much for written response, but there could be application kind of questions about those ideas. Okay, especially in terms of the 2 types of technology we addressed when we talked about the second law. When we talked about the second law, we talked about heat engines, like a jet engine, and we talked about heat pumps, like an air conditioner or a refrigerator. Okay, a heat engine harnesses the fact that heat will flow from hot to cold. Okay, so in a jet, you have the combustion area where the kerosene is burnt. Okay, it gets really, really hot. Air flows through the turbine as it's going from hot to cold, turns the turbine, and that generates thrust, okay, for the aircraft. A heat pump goes against the second law of thermodynamics because it forces warm air into the hot area in order to cool things off. Okay, so you can get around the second law of thermodynamics. Okay, essentially you can pay it off. Like the second law of thermodynamics can be bribed. Okay, and then you can break that law provided you have enough what? Energy. Yeah, you have to put energy in. You have to expend energy, okay, in order to go around the second law of thermodynamics. That is, you have to pump actively the heat out into the hotter area. It's very similar to active transport in the biology unit. If you're willing to expend energy, you can do things opposite the way they naturally flow. All right, so this is heat engine and heat pumps. Okay, those are 2 examples. Again, this is probably multiple choice kind of territory where you'd be asked to identify, you know, here's a description of a piece of technology. Is it a heat engine or a heat pump, or which law of thermodynamics is being applied here? All right, after we talked about thermodynamics, okay, and the types of energy, then we went to scalar and vector quantities. Why is it important for you to know whether a quantity is scalar or vector? Or let's say, how on the test is that going to be important? Rachel? Okay, units to an extent, yes, although speed and velocity, one is scalar, one is vector, but they both have the same units. They both are meters per second. A vector quantity has magnitude and direction. Okay, so that's the big difference, is they have magnitude and direction. But on the test, what's going to be important is not so much that you've memorized them all, although that's kind of important, but that if I'm asking a question, let's say that it's an acceleration problem, okay, and I give you the acceleration and I tell you it starts from rest and I tell you how long this takes, calculate the final velocity. Am I looking for a vector quantity or a scalar quantity at the end of that question? Is velocity scalar or vector? It's vector, okay? If you don't remember that, you won't put a vector on your answer, and then you'll get it wrong, okay? So that's where you need to know, is this a scalar quantity or a vector quantity? That way you remember to put a vector on. Or if it's a V equals D over T question, which is what we addressed with this, okay, then you need to know whether you're using displacement to calculate velocity or whether you're using distance to calculate speed, because those will be different numbers. Okay? And that can be a problem if we're not familiar with which ones are scalar and which ones are vector. Now, what I have here for WR, that's written response. That's what I was talking about just a minute ago. If I give you a problem and ask you to say calculate velocity or calculate speed, you need to understand, is that a vector or a scalar quantity? This V equals D over T, that's not going to be in the written response. Okay. Yes, there are some V equals D over T problems on the exam, but they're in the multiple choice. Okay, because that's an easy calculation. I don't need to give you 3 marks, okay, to do a V equals D over T calculation. 1. Right, so be ready for that. Could it also be part of possibly a graph question? Can you sometimes use V equals D over T with a graph? Possibly. If the graph has many sections, you might use V equals D over T. Okay, so that's another spot. You got to be familiar with how to use and manipulate that formula. All right, if they have the arrows over top, this V is velocity, this V is speed, this D is displacement, okay? This D is displacement, this D is speed. Or sorry, is distance, sorry. All right, so be familiar with those, okay, because they'll be important, okay, knowing scalar and vector quantities. Okay, other thing to remember, that displacement, which is a vector quantity, can be calculated by going final position minus initial position. That, a lot of times, comes into play on a position versus time graph. Especially one that may have more than one part. Okay, so it's got, you know, like a section that goes up and a section that's flat and a section that goes down and so on. Okay, if it asks you what's the total displacement or the average velocity over the whole trip, you'll need to use this. Okay, then after that we talked about acceleration. Okay, the formula for that is A equals VF minus VI over T. Obviously you don't have to memorize that. It is going to be on the exam. Okay, there is a written response item that is an acceleration problem. And expect that you're going to have to manipulate that formula in order to solve it. Is it worthwhile for you to go over your formula sheet from physics as part of your studying? Okay, it is. Not because I'm making you memorize the formulas. I'm not. I'm giving them to you. But you need to remember what they are and what they mean and when you use them. Okay, because I have a lot of times people come into an exam and then in the middle of the exam they put their hand up and they're like, Mr. Coder, what does this V stand for? And I can't tell them. Okay, if you don't know what that V and that formula stands for, that was your job. Okay, so you have to make sure that you look over those formulas and go, all right, I don't have to memorize this formula, but M usually stands for mass, okay, and V usually stands for speed if it doesn't have an arrow over top. It stands for velocity if it has an arrow over top, and so on and so on. Okay, make sure that you know what all of those things stand for in the formulas. Okay, is acceleration a vector quantity? Yes, it is. All right, so generally, when you have an acceleration problem, these are velocities. Not always, but often. Okay, then we spent a fair amount of time on the next topic. graphing. Okay, there are graphs in both sections of the final exam. Some of those graphs are simply read and interpret this graph. So what's going on in section A of this position versus time graph? Or tell me what the object is doing in section C of this velocity versus time graph. And so you'd have to be able to read and interpret, okay, what motions are going on. You'll also be asked to do some calculations from those graphs. Okay? If your graph is just a line, then you would be expected to use what formula most likely? What formula always applies to just a linear graph? Yes, y equals mx plus b. Okay, so you will have to use y equals mx plus b. Okay, you'll be asked to do some extrapolating. Okay, so if it says extrapolate, use y equals mx plus b. A lot of people got burned on this on their unit exam. Okay, because on their unit exam, remember I gave you that position versus time graph, and I had the equation for the line right there on the graph. And the first question was, what's the velocity of the object? And it was worth 1 mark. Why was it only worth 1 mark? Right, because the slope of a position versus time graph is velocity, and the slope was in the equation. Okay, you didn't have to calculate it. You just had to recognize that slope was the velocity of the object. Okay. The other thing that people got burned on was the next two questions, where the questions were worded like this. Using your graph, and I think it also said, and the equation given with it, or something like that. Okay, but if it says using your graph, you should probably use this formula. It's usually asking you to extrapolate. Okay, and if a graph is just one line, it's y equals mx plus b, extrapolate. Okay, if the graph has many sections, then you're probably going to have to do some other formulas, v equals d over t, or a equals vf minus vi over t, or something like that. Okay, but if it's just one section, linear graph, this is the equation for a linear graph. Okay, now, quick review. Y is the vertical value of any point. X is the horizontal value of that same point. Okay, M is slope, and B is y-intercept, okay, where your line crosses the y-axis. Important to remember what all of those pieces are. All right, the types of graphs we went over. Position versus time was the first kind that we went over. What kind of things can we get from a position versus time graph? Or what can I read directly off a position versus time graph? Which words did I just accentuate there? Time and position, right? Okay, I can read directly off of a position versus time graph the position of an object at any point in time. That's what it tells me. Okay, I can calculate a couple of other things from a position versus time graph. So what can I read off of it? Okay, well, I can I can read those two things. I can calculate velocity in a couple of different ways. If my position versus time graph looks like this, it has many different velocities or speeds on it, okay? Because the object is changing its velocity in this graph. So in that case, I would use v equals d over t, because it's not one simple line, okay? In that case, I would use v equals d over t, and to get d, I would probably have to use final position minus initial position. Okay, so that would be kind of a more complex kind of a graphing question. If my graph is just a single line like this, then I just need to remember that the slope of the line is equal to the velocity. Now, why does the slope of this line equal velocity? Because if I pick a point on this graph, okay, and the line, let's say, goes through the y-axis here. I think I kind of shorted it a little bit there, but okay. Then this point here is b, okay? This point here is y, and this point is x. Everybody all right with that? So if I manipulate for slope, for m, that's going to be m equals y minus b, because I would subtract b over to this side, divided by x. On this graph, y minus b is my final position minus my initial position divided by time. That's where that formula comes from. Okay, that's why the slope of the line equals velocity on this graph. Okay, so I can calculate three things off of a position versus time graph. I can calculate velocity, okay, using either v equals d over t or y equals mx plus b, depending on the kind of graph. And I can calculate displacement, pf minus pi, or I can calculate total distance traveled. And remember, distance is scalar, so it doesn't care whether I go forwards or backwards on the graph. So I would add all of these sections together. Essentially what I would do is go pf minus pi for this section, pf minus pi for this section, same for this, okay, and eventually end up with a bunch of numbers that I would have to add together, making sure I make them all, since it's scalar, I would make them all positive, okay? Whether they actually ended up being positive or not, okay, that's what I would do. Okay, is that ringing a bell for position versus time graphs? Okay, what was the other kind of graph we went over? Jade, what did we go over? Velocity versus time. Okay, so what can I read directly off of velocity versus time graph? Velocity and time. Right? So we could again run into two shapes or two kinds of velocity versus time graphs. One that has several sections that are different, or one that's just linear. Okay, we would solve for things differently depending on what kind of graph we had. Okay. One of the things that I can calculate from a velocity versus time graph is acceleration. If that graph is linear, like this one, then the slope of the line is the acceleration. For the same reason, the slope of the line in the last graph was velocity. Okay, so we'll go over that here in just a sec. Remember that the formula for acceleration is Vf minus Vi over t. So if I got a graph that's got lots of parts, I would take the final velocity, subtract the initial velocity, and that would give me the average acceleration over the entire graph. Okay, remember that this formula, however, is derived from this one. Okay, because we have speed or velocity on the y-axis and we have time on the x-axis. So when I solve for slope, the same way I did in the last graph, I'm going to end up with y minus b divided by x. Well, y is a velocity, the final one, b is the initial velocity, and x is time. Okay? So it's the same idea as it was on the last graph. All right, there's one last thing I asked you to calculate from a velocity versus time graph, and this is the one that gave people the most trouble. Anyone remember what it was? Displacement, right? Okay, I asked you to calculate displacement from a velocity versus time graph. Okay, to do that, you take the average velocity and you multiply it by the time, which ends up being the areas of all the different shapes that would be created by the graph. All right, so on this graph here, if I had a line that looks like this, okay, so it goes over, then it goes up, and then it goes over, okay, I would calculate displacement by taking the average velocity for each part and multiplying it by the time. So for this first part, the average velocity is 3 because it travels at a constant velocity of 3 meters per second for 2 seconds. So 3 times 2 is 6. Everyone follow what I did there? Right? Then I've got this triangle here, okay, this small one, that goes from 3 to 7. Okay, so it increases its speed from 3 to 7 meters per second, which means its average velocity was halfway in between there. So the height of this triangle is 4. That's the change in velocity. Okay, base times height over 2, okay, gives me the same thing. So I have 2 seconds as my base, and my height here is being 4 divided by 2. 2 times 2 is 4. Then I've got this big rectangle underneath that goes all the way to 10, right? It's got a height of 3 and its length is 8. Okay, so 3 times 8 is 24. This box up here has a height of 4 and a length of 6. 6 times 4 is 24. Now I've got all those areas calculated. Now I add them up. I've got my total displacement, okay? Because I've taken the average velocity in each section and multiplied it by time. Is that something I'll probably ask you to do? Okay. Would the graph have a whole bunch of sections, or would it be a simpler graph? Probably simpler. Okay. In the interest of time, what I'm interested in on the final is, do you still remember how to do that? Okay. Not, can I give you a question like I gave you on the worksheet for graphing that had you calculate 20 different areas of tiny little shapes? Because that's not an effective use of time on a final exam. Okay. I can find out whether you know how to do this with a 2-section graph. All right. Then we went into this work energy theorem, which is, without a doubt, the most important concept in physics, possibly science. Okay, remember that the work energy theorem states that work is a change in mechanical energy. Right? That's what work is. So if there's a multiple choice question about work, remember, that's the definition of work, a change in mechanical energy. All right. The other formula we used to calculate that was force times distance. All right, so there's going to be some multiple choice questions about the work energy theorem that are going to check your understanding. So they could be situational kind of application type questions, like, what would happen to the kinetic energy of, let's say, like a bullet when it hits a bulletproof vest? Okay, well, its kinetic energy would decrease because it would exert a force on the vest over a short distance and its velocity would change, resulting in a lower kinetic energy. Okay, something like that. Everybody follow? Okay, so there could be multiple choice questions, kind of like that, with just kind of situational kind of things. Okay, and then there's obviously going to be a written response item about work energy theorem because we spent a lot of time doing work as a change in energy problems. On your unit exam, you had one that was a change in kinetic energy, and you had one that was a change in potential energy. Okay? Final exam, I don't have time to ask both, but I'm asking one. Okay? But you need to know how to do both because I'm not telling you ahead of time which one I'm asking about. Okay, so work is force times distance, which is also a change in mechanical energy. That mechanical energy could be potential or kinetic, as I was saying there before. And I'll go over a couple of examples of that once I've gone through the rest of the stuff here. Okay, I'll go over an example of a potential energy one and a kinetic energy one here in a few minutes. Okay, on your unit exam, that was a 6-mark problem. Okay, so that's worth an investment of time on your final. Okay, so other things to remember about work energy theorem, okay, that delta E means final energy minus initial energy. So final kinetic minus initial kinetic, or final potential minus initial potential. What very often was our initial kinetic or potential energy? What number? Yeah, very often it was 0. Okay, simplified the question a little bit. Remember that potential energy, gravitational potential energy, is mass times gravity times height. Okay, again, you don't have to memorize that formula. It's on your formula sheet, but know what everything means. G is something we only use in this unit. Okay, so G is 9.81. And then that kinetic energy is 1/2 mv squared. There could be some multiple choice items about those as well. Okay, just the 2 types of energy. The example I gave you in class was the relationship between speed and stopping distance. Okay, like why you should absolutely not go faster than 30 kilometers an hour in a playground zone. Okay, because as you increase your speed, the amount of energy you have increases exponentially. That means it takes you exponentially further to stop. Okay, that's work energy theorem. It has to do with kinetic energy. Okay, things like that. After that, we talked about the law of conservation of mechanical energy. What context did we usually have these in? Like, what was the most common kind of problem for conservation of energy? The rollercoaster questions, okay? The rollercoaster questions are conservation of mechanical energy kind of questions, okay? So we got to remember that the law of conservation of mechanical energy says the mechanical energy never changes. The initial mechanical and the final mechanical are always the same. Okay? What can change is how much of that mechanical is potential and how much of it is kinetic. Right? So the example we had usually was a roller coaster. So what we're going to look at today is an example that's just like a box sliding down a hill. Okay? We also have to remember that mechanical energy is the sum of both potential and kinetic energy. We add those two up to get mechanical energy. All right, so here's our example of a law of conservation of energy problem. I've got this 20 kilogram box sitting on top of a 20 meter high hill. Its initial velocity, or initial speed, sorry, is 4 meters per second. A little while later, a little further down the hill, its speed is 10 meters per second. I want to find out how far above the bottom of the hill it is now that it's moving at 10 meters per second, because it obviously slid down the hill a little ways. Okay, so the first thing I got to do is recognize the energy isn't changing. EI equals EF. The next thing I have to identify is, do I have both kinds of energy at both points or not? Okay, so up here at the beginning, do I have potential energy? Yes, I'm 20 meters above the bottom. Okay, do I have kinetic energy? Yes, I'm moving at 4 meters per second. All right, so I know that at the beginning, I have both kinds, EP plus EK. At the end, do I have both kinds? Probably. We don't know for sure, but we have to assume that the question wouldn't ask us to calculate the height if the height was going to be 0. Okay, so we have to assume it probably has a height here. The other thing is, look, it didn't increase in speed very much, okay, and it has a 20 meter hill. It's probably still got some room to go, right? So we're looking for our final height, and we know we have both kinds of energy at both points. Okay, so that's our next step. Okay, that our initial potential plus our initial kinetic equals our final potential plus our final kinetic. Now I'm looking for the final height, which is part of which of those 4 terms? Will, which term? Height's part of which kind of energy? Potential. Okay, am I looking for the initial potential or the final potential here? Right, so I'm looking for EPF. So I want to get EPF by itself. What should I do with EKF? I should subtract it over to the other side. All right, so that's my first step. That gets the things kind of set up before I plug in all the variables and it starts to look confusing. Okay, so we have initial potential plus initial kinetic, in other words, the mechanical energy, minus the final kinetic energy should equal the final potential. So that should be an F there. Okay, should equal the final potential energy. All right, now my next step is plug in the formulas for these terms. So potential energy is m times g times h. Kinetic energy is 1/2 mv squared. So I plug in the formulas. Okay, so m times g times h plus 1/2 mv squared. Sorry, and these are the initials, so mghi, 1/2 mvi squared minus 1/2 mvf squared. Okay, gives me my final potential, which is m times g times hf. Now, I gave you the mass in this question as I would on any question on an exam, but do you need it? No. You can leave it in there, but you don't need it because it's in every term. Okay, so I'm going to cancel it off just to make my life a little bit easier. So m's are gone. I need to get hf by itself. Okay, so just to kind of reiterate what we're doing here. Okay, the m's are gone. I need to get hf by itself. What do I have to do with the g? I have to divide it over to the other side. Okay, so that's my next step. I divide both sides by g, and now I've got hf alone. Okay, big thing to remember here, these two g's do not cancel. Okay, there's a G on the top, there's a G on the bottom, but they don't cancel because this is an independent operation. All right. Next step then is that I need to plug in my numbers. Right, so that's going to be 9.81 for G. Okay, for HI, it'll be 20. Okay, for VI, it'll be 4 meters per second. For VF, it'll be 10 meters per second, and then divide by 9.81. So it'll look like this. Okay, when we do that operation on our calculator, okay, it's probably best not to try and do it all in one calculation because sometimes we mess up the order of operations then. Okay, so if I was calculating this, okay, I would say, all right, 9.8, whoop, can't do it from that side. 9.81, okay, times my initial height, which was 20. Sorry, 9.81 times 20, okay, gives me that, plus 0.5 times my initial velocity squared, okay, 4, gives me 204, and then I'm going to subtract the final one here, which is 1/2 of VF squared, so minus 0.5 times 10 squared. Okay, then I'm going to divide that by 9.81. Okay, so the final height is 15.7 meters. Didn't fall very far, right? Didn't slide down the hill very far. Only about 4.25 meters. Okay. 15.7 meters is the final height. Is that ringing a bell? Okay, there is one of those on the final exam. And it's 8 marks. It's not something we want to miss out on. And the last thing we talked about in this unit, okay, after we did law of conservation of energy, was efficiency. Okay, efficiency is the percentage of the actual, of the input work that you actually get out. So you divide actual work by the amount of energy that you put in, and you'll get the percentage of it that was used to do what you wanted, which is the efficiency. Okay, the smaller energy number is always the one that goes on top. Okay, you never get all of the energy out that you put in because nothing's 100% efficient. And there's a couple of multiple choice items about that. Okay, questions on any of that stuff? All right, let's have a look at a couple of work energy theorem problems here. All right, so our first work energy example here is asking what force is used to throw a 1.5 kilogram ball over a 1.5 meter distance to a height of 21 meters. So our first task is to write down our givens. Okay, our givens are that we're given a height, 21 meters. We're given a distance, 1.5 meters. We're given a mass, 1.5 kilograms. And we're being asked to find a force. In this question, what kind of energy is being changed about the ball? Okay, so potential energy is changing about the ball. We know that because its height is changing. Okay, and that's what we're told, is that it's going from some unknown height, which we would assume would be the ground, okay, to 21 meters. So first, the next thing we write is work is a change in potential energy. Now, the formula for work is force times distance. That's good because I'm being asked to calculate force and I was given a distance. Change in potential energy means final potential energy minus initial potential energy. It doesn't outright say it anywhere, but generally when you throw things, you're standing on the ground, which means the initial height of this would be 0. So if HI is 0, this whole term is also 0, and I can just eliminate it. I'm looking for the force. So what do I have to do with D? I have to divide it. Right? So I divide both sides by D. It comes over here, and now I can calculate my force after I plug in my numbers. So force will equal 1.5 kilograms times 9.81 meters per second times 21 meters divided by 1.5 meters. All right, so 1.5 times 9.81 times 21 divided by 1.5. Okay, 206 newtons would be the force that I had to use. Okay, ringing a bell. All right, we'll do one where the kinetic energy changes as well. All right, so in this example here, we're looking for the final speed of a car that is accelerated by a 500 Newton force over a 15-meter distance if its mass is 1,000 kilograms and it starts from rest. Okay, so here's what we know. We know the force, 500 newtons. We know the distance, 15 meters. We know its mass, okay, and we know that it started from rest. If it started from rest, what's its initial kinetic energy? 0, right? Okay, so in this question, we're changing the kinetic energy by doing work. So force times distance equals 1/2 mvf squared minus 1/2 mvi squared. But as we already said, vi is 0, so there's not even any point in writing it down. Okay, I want to get vf by itself. So what do I have to do with the 1/2 and the m? Gabe, what do I have to do with them? Divide them over to the other side. Okay, that gives me VF squared. I want just VF. So what do I need to do to both sides? Ethan, what do I have to do to both sides? Square root them. All right, so that gives me my correct formula. So VF will be the square root of 500 newtons times the distance, which was 15 meters, divided by 1/2 times the mass, 1,000. Okay, if we punch all that into our calculator, okay, we have 500 times 15, okay, divided by 500, which is 1/2 of 1,000, gives us 15, and then I have to square root that. All right, car doesn't accelerate very much, but you got to remember, we didn't use very much force, and the car is really, really heavy. Okay, so using a small 500 Newton force over that kind of distance isn't going to give us much change in speed. Everybody follow what we did there? All right. Okay, a couple other questions that my period 1 class asked. We'll just kind of quickly go over what a few of the things they asked. They asked, can you go over a couple of y equals mx plus b calculations? Okay, so on a position versus time graph, okay, where I have meters on the y-axis and seconds on the x-axis, okay, I could give you a question like this. I show you a line, and I give you the equation. Let's say that the equation ends up being y equals 4.5 times x plus 6. Okay, the 4.5 is the slope. Okay, 6 is the y-intercept. Okay, so the 4.5 is actually the velocity of the object. If I want to calculate, so the question then would probably ask me, calculate the position of the object after 50 seconds. If they tell me after 50 seconds, have they given me a y value or an x value? They've given me an x value. And they're asking me to calculate the position, which is on the y-axis. So I'm being asked to calculate a y value, and I'm being given an x value. So I just plug my numbers in. I'll do y equals 4.5 times 50 seconds. okay, the x value they gave me, plus 6, the y-intercept. That gives me 231 meters. That would be the position of that object if it traveled for 50 seconds. Okay, and this is what burned people on the unit exam. Okay, a bunch of people, we had exactly this question, and a bunch of people used v equals d over t to calculate all this stuff. The problem with using v equals d over t is it doesn't take into account that you started somewhere other than 0. Okay. The other problem with that question on the unit exam was that the first question was a 1-mark question asking you what's the velocity of the object. Okay, and a bunch of people went v equals d over t to calculate it, except that all they had to do was write down the slope of the line, slope of the line's velocity. Okay, and that's what that question was asking, was did you remember that? Okay, the other way that I asked on the exam, and probably will on the final, is I could ask you how long it would take to reach a position of 200 meters. So in this case, I've given you a y value, and I'm asking you to calculate an x value. So we manipulate to solve for x. So if I'm going to solve for x, I subtract 6 over here, and then divide by 4.5. Okay, so y minus b over m. So 200 minus 6 divided by 4.5 gives me that would take 43.1 seconds. All right, is that ringing a bell? Definitely going to be asked to do y equals mx plus b calculation on your final exam, so be ready for it. Okay, and then I asked, they didn't have any more physics questions, so they asked about a precipitates question, so we'll just set it up the way I had it initially. Okay. If I was asking to do a solubility question, so this is from chemistry, it would probably look something like this. I would give you the reactants for a double replacement reaction. Okay, and I would say, predict the products and tell me which, if any, are not soluble. Okay, so the first thing we have to do is do a double replacement reaction prediction. Double replacement reactions, we swap the metals. So our products are going to be lead with iodine and sodium with nitrate. Okay, I have to drop and swap these because they're both ionic compounds. So this is a +1 and this is a -1, so that compound is fine. Okay, this is a -1. Lead can be a +2 or a +4. Which one is it? It's a 2. Okay, the nitrate here comes as a 2, so that means that the lead must have been a 2. So we'll have PbI2 on this side. Now I go to my solubility chart. Okay, and I look on my solubility chart, and it says that all nitrate-containing compounds are soluble. That means this must not be. Okay, and if I look at iodine and I go down the row or down the column, sorry, we'll find that lead is in that lower column. Remember your solubility chart, okay, looks like this. So we would have like a column with I and usually Cl and a few other things are in there, and it'll say most, and then down here it would list things like lead and mercury and things like that. So this would be not soluble. Okay. All right. Anything else you want me to cover? That would be a multiple choice question, yeah. Okay. Anything else you want me to cover? Any other questions that you guys have? For mini unit, I'll take it for mini unit. Great. Okay, it's an acceleration question. I know which one you're talking about. Okay. So it would look something like this. Something like that. Okay, it would either give you a time or it would ask you how long would it take to reach this speed, something like that, right? Either way, it doesn't seem like it gives you very much information, but it does. If something falls, how fast was it going at the start? That'll be the acceleration, okay? That's one of the other things we need to know. Anytime an object is falling, its rate of acceleration is 9.81 meters per second squared. What was its initial velocity? Anytime you drop something or something falls, okay, its initial velocity is 0. The only way it can be anything other than 0 is if it is thrown or projected in some way. And they tell me the time. So the question doesn't outright give me numbers, but it gives me a situation where I need to recognize I was actually given more numbers. Okay, anything falling falls at 9.81 meters per second squared. Okay, and if it falls or is dropped or something like that, it's VI. If it says it was thrown, then you have an initial velocity of something else. Okay, so now it just becomes an A equals VF minus VI over T calculation, and I'm solving for VF. So I multiply both sides by T, and I add VI to both sides. So if I actually had a VI, I would put the number in there. Okay, in this case it's 0, so I can cancel it. Okay, so T times A, 3.5 times 9.81, and we've got our final speed. Okay, 34 meters per second, something like that. Does that answer your question? Okay, Rachel? Acids in the bio? Oh, right. Okay, the hormones, the plant hormones. Okay, yeah. All right, so plant hormones are as follows. Auxins. Okay, auxins cause cell lengthening. Okay, in other words, like growth. Okay. Okay, gibberellins cause secondary growth. Okay, what I mean by secondary growth is like width. They make the stem essentially get fatter. Okay, it's how the plant supports more growth. That's why like dandelions that get sprayed get all coily and fall over, because they secrete a whole bunch of this but don't use any of this. So they get too tall to support themselves and they fall over and die. Okay, so that's for secondary growth. I very rarely ask about gibberellins because they're not a very important hormone. Okay, and then we had we had cytokinins. Okay, and they cause cell division, so growth of new cells. Ethylene. Ripens fruit and ages plants. And then we had abscisic acid. Okay. Causes dormancy by disrupting the production of chlorophyll. That's why leaves change color. They don't have any chlorophyll in them. Plant stops carrying out photosynthesis, stops transporting water, and assumes a dormant state. Okay. That good enough, Rachel? Okay. Other questions there, guys? Really, all you need to know for those is just know them. Like if I show you a picture, it's this hormone or it's that hormone. Okay. Which one of those is involved in tropisms? Auxins, right? Okay. Other questions? Okay. Tips for your exam. Which section should you do first? Yeah, I mean, it's your test. You can do it in whatever order you want, but I would do the written first because it's going to take the longest. And there's nothing worse than getting the 10-minute left warning and seeing that you have 6 out of 15 written response items left to go. Okay, it's way better to get that 10-minute warning with 15 multiple choice questions left to go, because you can probably finish that. Maybe you can't, but you can at least fill in answers, right? You can go A, C, D, C, B or something like that when the time runs out. Okay, at least multiple choice is something you can accomplish when pressed for time. Okay? If you're staring down 4 or 5 written response items that all require a paragraph answer, you're not going to finish that, and they're worth more marks. So I would do the written first. You don't have to do it in order, and in fact, I wouldn't. Okay? Pick the ones that you know how to do first and do them. Okay? That will prevent the one thing that gets people all the time, and that's stalling. Okay? The number one thing that I see on final exams from people who don't finish is that they stalled on a question. That is, they read the question, didn't know how to do it, and sat there and stared at it. And it's really easy to lose track of how much time you sit and stare at a question for. Okay? If you don't know how to do a question within 30 seconds of reading it, move on. Okay? Because I have actually come up to people in the exam after walking by them twice, which would probably be like a 5 or 10 minute interval as I'm kind of patrolling the exam, and they're still staring at the same question. At that point, I usually tap them on the shoulder and say, you should probably move on. Okay? Because I've actually had in an exam that I wasn't supervising, I came in there at the end to collect the exams, and here's a kid in tears who did the multiple choice first, got to question 4 in the written, didn't know how to do it, and stared at it for a half an hour. Okay? If you waste a half an hour accomplishing nothing but staring at a question you don't know how to do, you're not going to finish this test. Okay? This test is challenging, and it's going to require most of the time, if not all of it. If you waste a whole bunch of it accomplishing nothing, you're going to be in trouble. Okay? So if you don't know how to do it, move on. It'll still be there at the end. Okay? And you'll find you have some time for it at the end. And most likely, after having done the rest of the test, some other question, maybe in the multiple choice, will trigger something for you for that question. And if it doesn't, in the end, all you didn't do was that question, as opposed to the 6 after it that you didn't get to because you stared at it. Okay? So please don't stall on a question. If you can't do it when you first read it, move on. If you can't do it at the end, okay, you missed that question. That's not the end of the world as long as you got all the others done. Okay? So you're going to have to manage your time effectively on the test. Now, I would suggest that you have a watch. Okay? And I would even suggest that you take it off and set it on your desk, right? Like right in front of your test, so that you are, seeing it out of at least your peripheral vision most of the time, and you have an idea of what the time is. I mean, yes, there's clocks in the gym, but it's pretty easy to get head down focused, okay, on a final exam and not look at the clock. So have a timepiece on your desk that you can see fairly clearly all the time, because that will help you manage your time. Okay, because a lot of people, they get done the written response and like, yeah, I'm done the written response. They look up and like, oh man, I really should have looked at the clock, because man, like an hour and 45 minutes have gone by and I got 50 questions to do in 15 minutes. Okay, which isn't impossible. The multiple choice questions are easier. Okay, but it's still moving pretty fast. Okay, realistically, the written response should probably take you between, let's say, an hour to an hour and a half. Okay, if after an hour and a half you haven't moved on to the multiple choice, you're probably a little bit behind schedule. Okay, you can probably do the multiple choice at least a rate of 2 questions per minute. Okay, sometimes even 3. Okay, you probably won't average 3 questions per minute, but I think on average you can average 2 questions per minute in the multiple choice pretty easily. Right? But if after an hour and a half you haven't moved on to the multiple choice, you should probably look at what you're doing. Okay, that's why I say it's really important to manage your time. So know then for sure that this test is challenging. Okay, I did the key the other day and it took me about 40 minutes. Okay, so that's going to mean it's challenging, right? It's not the easiest one I've ever written. It's also not the hardest one I've ever written. Okay, but it's challenging. So you need to be ready for it. You need to be well prepared when you come in. You need to take it seriously. You have to have a healthy dose of fear. Okay, there's a healthy amount of fear, and there's a destructive amount of fear, and then there's lack of fear. Destructive and lack of can be equally destructive. Okay, if you have no fear, you walk out into traffic. Okay, like that's not, you need to have some fear that cars can run you over. Okay, if you have a destructive fear, you stay in your house all the time and never leave. Okay, those are the two destructive levels. Healthy amount of fear is motivating. Okay, you should be motivated to prepare well for this test and spend time preparing for it. Right. Now, remember your help times tomorrow, 8:45 to noon. Okay, Friday, 8:45 to noon with a possibility of 1 to 2 as well. Okay, and Monday, all day. Okay, 8:45 to 3 o'clock. Okay, if you come in during the lunch hour, I'll be eating, but if that's the only time you can pop in and see me to ask a question or two, pop in anyway. Okay, but those are the times I'll be available for you to come and ask for help. Please make sure that you take advantage. Right. If you come in for help, no, there won't be any desks in here. Okay, so there's only like the chairs and the table. If a whole bunch of you are planning on coming in at the same time, some of you may want to bring lawn chairs, or you're going to be sitting on the stools from the chem lab, which are not very comfortable. Okay. All right, any other questions? All right, well, you still got some time to do some final exam prep, work on that final exam review package that I put on Google Classroom, okay, any of that kind of stuff, but let's use our time wisely here.